Today the disk ran out of space and the recording of today's lecture was lost. So what I'll do is I'll run you through the notes to explain what we did in the lecture. Today's lecture is about the Z transform, whereas last time we talked about the Laplace transform. They're very similar, so a lot of what we cover will be very easy, and basically the differences will be what you need to internalize here. So the Z transform is for discrete time signals, and the Laplace transform was for continuous time signals. Here we have the formula for the Z transform. This is an infinite sum. There's the signal x. And here Z is an arbitrary complex number. So this transform is a function of Z. For a given Z, you do this infinite sum, and you get a complex number. Again, like the Laplace transform, the domain is complex, the range is complex. And like the Laplace transform, this may converge only for some values of Z. We'll want to know for which Z does it converge. That'll be a part of an important feature of the Z transform, is where its region of convergence is. So it looks a lot like the Laplace transform or even the Fourier transform, but there's a difference here. We notice that we have a Z as the base of the exponent, whereas in the Laplace transform we had an e to the negative st. So really the difference is this is the same as the Laplace transform, but where you've replaced e to the s by z. Now e to the s, being an arbitrary complex number, can map over to a complex z. So this is just sort of a different parameterization. It turns out this is more relevant for discrete time, and we'll talk a little bit about why we would do such a substitution, why we would take the parameter out of the exponent and just make it the base. So for the Laplace transform, we saw that a deterministic, we saw that the real part of S is what determined if it was going to converge. Because the real part of S had to do with this real exponential that shaped your signal. So for example, if you were thinking of S as a real part sigma and an imaginary part, which we'll call I2 pi f, then it was sigma that determined if it converged, because really it was e to the sigma t that was multiplied by your signal, and then essentially a Fourier transform. And if you don't remember those steps from last time, that's okay. We'll do them again right here. So really, if z equals e to the s, which would equal e to the sigma times e, whoops, that's not sigma there, that's e. I'll correct that. E to the I2 pi f. Then the magnitude of z is e to the sigma. So sigma determined if the Laplace transform was going to converge, and we'll see that the magnitude of z is going to determine if the Z transform converges for this exact reason here. So let's compare this to the Fourier transform. If we let Z equal a magnitude A, let's say a real number, times e to the I2 pi f, all right, so this is just taking a complex number to its magnitude and its phase, then the Z transform evaluated at this parameterization, we plug it in, and you immediately see that this is just the Fourier transform of the signal multiplied by an exponential function, a real exponential function. So again, just like the Laplace transform, we basically are reshaping our signal by multiplying it by an exponential function and then taking a Fourier transform. And the particular reshaping is just going to depend on the magnitude of Z, this A parameter. So for example, if we let A equal 1 and we just evaluate the Z transform at e to the I2 pi f, that's exactly just the Fourier transform of our discrete time signal, evaluated at f. Now, since we've emphasized that it's the magnitude of Z that determines if it's going to converge or not, then it's clear that the region of convergence is going to just be a ring. It's going to just depend on the magnitude of Z. That means only the radius to the origin. And in particular, it's going to be bounded, if that magnitude is bounded between two numbers. It's not always necessary that you have both borders of this ring. It could be everything inside of a circle, or everything outside of a circle, or everything inside of a circle could be the region of convergence. So now let's again just try to conceptualize this transformation from the Laplace S-plane for the Laplace transform and this Z-plane for the Z transform. And let's think about this transformation Z equals e to the s. notice that vertical lines in the Laplace transform, if you go through the substitution, they become circles centered on the origin. For example, take the imaginary axis. If you take e to an imaginary number, you get something of magnitude 1. So that's this unit circle. This blue line is a unit circle. Notice it has radius 1. That blue imaginary axis becomes this blue unit circle. And even we can become more specific about that. We can say, well, the point 0, the origin here, where does it map to? E to the 0 is 1, so it maps to this point here. Let's go along this imaginary axis and look at the point I pi. E to the I pi is negative 1, so that's this point. And as you move along this blue line, you're moving along the unit circle in the positive phase direction. Okay? If you move down the imaginary axis, you're moving in the negative phase direction. Of course, we have some periodicity here, because if we went to 2 pi, that would be back to 1. E to the 0 and e to the 2 pi and the I2 pi are the same. So you'd have gone all the way around the circle. So if you keep going up this imaginary axis, you keep going around this unit circle multiple times. All right? Which, so that actually points something interesting out. That is that notice that notice that for discrete time, Fourier transform, you always have a periodic Fourier transform. So here's one reason why the Z transform, it's nice to parameterize it as Z equals e to the S. Because this automatically indicates that there will be some periodicity in this Laplace transform or in the Fourier transform. Let me make that a little more clear. Remember that the Fourier transform lived on the imaginary axis of the Laplace transform. That's something we talked about last time. That if you just substitute real part of S equals 0, you get the Fourier transform. So you go along this line and you get the values of the Fourier transform. Well, because of this mapping, we'll see that it's clear that the Fourier transform in the Z is the unit circle of the Z transform. So if you just plug in e to the I2 pi f to the Z transform, then you get the Fourier transform. We already pointed that out right here. You plug in e to the I2 pi f, and you get the Fourier transform. So what that means is, if you look at the values of the Z transform going along the circle, they will tell you that they will be the values of the Fourier transform. And of course, if you go around the circle more than once for higher frequencies, you get back to the same values, which is exactly what we expect for the discrete time Fourier transform. We knew it was periodic, and this parameterization, the Z transform representation, implicitly shows that it's periodic, because as you increase the frequency, you go around the circle and you get different values for the Fourier transform, but once you get to frequencies greater than 1, you repeat. Okay, so that's one of the nice reasons why the Z transform is parameterized this way, because it implicitly shows you that the Fourier transform will be periodic. All right, let's go on and look at some let's look at the properties we had for the Laplace transform. If our signal is right-sided, then the region of convergence, in this case for the Z transform, has no outward boundary. And this is all the same intuition as the Laplace transform, so I'll just go through these properties. If it's left-sided, the region of convergence has no inner boundary, except maybe it'll have a pole at Z equals 0. So this is the only weird exception for the Z transform. The Z equals 0 point, even if it's a left-sided signal, the Z equals 0 point might technically not converge. Think about the Z equals 0 point as, in the Laplace domain, that's like the infinite horizon as the real part of S goes to negative infinity. So, there may be a sort of a pole in some abstract sense in the infinite horizon. That did not affect the region of convergence for the Laplace transform. But that infinite horizon becomes the point Z equals 0 in the Z domain. So what you need to remember there is, it's okay if the Z equals 0 point might not converge. We'll still talk about that as if there's no inner boundary. And because a left-sided signal has no inner boundary, but it might still have a pole at Z equals 0. Now, similarly, if something has finite duration, we know that now it should not, the region of convergence should be the whole space. here. And in discrete time, there's no way for it to not be any of the space because there's no vertical asymptotes in discrete time. So for finite duration signals, it converges everywhere. Again, with the exception that maybe at z equals 0, it doesn't converge. Okay, so that's kind of the exceptional point. Now, stability. We know that a signal, well, let's say the impulse response of a system that is stable has the following property. If it's stable, then the unit circle is in the region of convergence. Remember, the unit circle is where the Fourier transform lives. So it's like saying, if it's stable, the impulse response will have a Fourier transform. Okay? Now, if it's, and this is if and only if in the following sense. If the unit circle is in the interior of the region of convergence, then it will be stable. So the only ambiguity is the boundary. If the unit circle is on the boundary of the region of convergence, then it may or may not be stable. But otherwise, this is if and only if. So now let's see. Let me just comment on why. I've already talked a little bit about this, but why substitute z equals e to the s for discrete time? After all, wouldn't it be simpler to just have a Laplace transform for both continuous and discrete time? We have a Fourier transform for continuous and discrete time, and the only difference was changing integrals to sums. So why have a whole different transform for discrete time in this case? Well, I've already said that this substitution of z, it emphasizes the periodicity. In fact, you can understand this as aliasing is sort of built into the z transform. You don't have to think about aliasing anymore. Okay, but a more important reason for this substitution is that the systems we care to analyze will have rational z transforms. So it's going to be very nice. The systems we care about will have if they're continuous time, they're going to have a rational Laplace transform. If they're discrete time systems, they're going to have a rational z transform. This is only true because of the definitions we're using for Laplace transform and z transform. Okay, you'll notice something about the Fourier transform notation in the textbook. You probably noticed they don't express the Fourier transform as x of f the way I do. I use capital X of f for both discrete time and continuous time Fourier transforms, and they use different notation. For the continuous time Fourier transform, the textbook says x of I 2 pi f. All right, and for the discrete time Fourier transform, it says x of e to the I 2 pi f. Now, I know that confuses many people, that notation there. But let's notice something. And by the way, they don't actually use I 2 pi f. They substitute j for I, and they substitute omega for 2 pi f. So, okay, so they say x of j omega, or x of e to the j omega for discrete time Fourier transform. But now you can see where that notation comes from. They're just using the same notation for the Laplace transform. This is the Laplace transform where you plug in I 2 pi f for s. And this is the z transform where you plug in e to the I 2 pi f in place of z. Let's go back and notice what we already observed, that if you plug in e to the I 2 pi f into the z transform, you get exactly the Fourier transform evaluated at f. So the textbook just adopts this notation from the beginning for the Fourier transform. Okay, now let's try to understand some of these properties of the Laplace and z transforms. And they're going to be just like our Fourier transform properties, so they'll be very familiar, easy to remember, and they'll even be the same as each other. So I'll just give the property for the Laplace transform, same property holds for the z transform. First, we have linearity, and that's pretty obvious because of the definition. So if you take a linear combination of two signals, you get the same linear combination of their Laplace transforms. For convolution, we have the most important property, the convolution property. If you convolve two signals, then you get the product of the Laplace transforms. Great, so that's exactly what we saw in the Fourier transform. Of course, we care about convolution because we care about LTI systems. Now, as a little aside, I want to point out something that's fundamentally related to this convolution rule. You remember that we talked about if we have an LTI system, which does a convolution, we talked about something being an eigenfunction or an eigensignal. And that meant those are signals that when you put them into as the input of your system, the same signal comes out with only a constant scaling. Okay? And it turned out that these complex exponentials, e to the I2 pi, some constant frequency f naught times t, so this is a complex exponential, those were the eigenfunctions of any LTI system. It wasn't even for a specific LTI system. Any LTI system will have these same eigenfunctions. And that is fundamentally the reason why the Fourier transform is so powerful, because the Fourier transform separates your signal into these components. Okay? And in fact, the scaling factor was simply the Fourier transform evaluated at f naught. So this is a very fundamental, important concept about the Fourier transform and LTI systems and about this convolution rule. Well, it turns out that complex exponentials, these of this form, are not the only eigenfunctions. In fact, take any e to the st where e is an arbitrary complex number, that is still an eigenfunction. So here, s has not only an imaginary part, otherwise it would be the same as above, but it might have a real part. And when you put in such a thing, so in other words, if s has a non-zero real part, then this is a growing or shrinking complex exponential. So it's got a rotating part, and it also has a growing or shrinking part. But when you put something of this form through any LTI system, you get the exact same thing back out times a constant. And that constant in this case happens to be the Laplace transform evaluated at that point. This would, for discrete time, it would be the same thing, but it would be with the Z transform. Okay, so that's nice concept. Now let's look at some more properties. We have a derivative property for continuous time. The derivative of a signal is simply that changes the Laplace transform simply by multiplying it by s. It's as simple as you can imagine. Very, very nice rule. The integral property, if you integrate from negative infinity to t, it's the exact opposite. You divide by s. Now, when you divide by s, by the way, that adds a pole. If this was a rational Laplace transform, that adds a pole at s equals 0. All right. Now let's look at a time shift property. First of all, in continuous time, and this is again just as we'd expect. If we delay our signal by cap t, we just get e to the negative cap t s times our original Laplace transform. So this is just like we had with the Fourier transform. It's just that s is there instead of I2 pi f. Now, we're actually not going to use this continuous time shift property at all. But we are going to care a lot about the time shift property in discrete time. So let's write this out. It's the same property. If you delay by an integer or advance by an integer, let's use cap n to denote the delay, then the Z transform is just the original one times Z to the negative n. Notice that this rule is exactly the same, but you've replaced e to the s with Z. Okay? So it's the same rule. All right. Now let me point out all of these little notes I've put here that I haven't talked about yet. First of all, a quick note about this continuous time shift property and the discrete time one. I said that we'll care a lot about this discrete time shift property. It turns out that that's going to be significant for systems we care about. In continuous time, we're going to not be looking at time shifts. Notice something interesting. Because of this change to Z, this is actually going to be, if x of z was rational already, then this is still going to be rational because you're just multiplying by z to a negative or positive integer. Okay, so this is still going to be rational. In the continuous time case, it was not rational. This is not a rational function of s. Fortunately, we don't actually care about doing these time shifts for continuous time systems. Okay, for the scope of what we're going to discuss. All right, nextly, I need to point out that these formulas, so far, all I've mentioned are what happens to the expression of the Laplace or Z transform. I haven't mentioned what happens to the region of convergence. Region of convergence is an extremely, it's an important part of the transform. So we need to know what happens to the region of convergence. Let's start at the beginning here. For both of these properties, linearity and convolution, the resulting region of convergence is the intersection of the two regions of convergence, the one for x of s, the one for ys, okay, for both of these. So it makes sense for the linearity case. You can't converge if each part didn't converge. Okay, so you need to be within the region of convergence of each part separately, which is what the intersection is. It may be that you get something larger than the intersection. The resulting region of convergence can be actually larger. I only listed that as the intersection, but in fact, it's possible that you're lucky in the linearity case or the convolution case, and that you get some cancellation. Imagine that you subtract something that doesn't converge from itself, okay, and now it does converge. So you might get some cancellations. The easiest way to think of that is you might get poles that somehow cancel with zeros or something. You might get poles that go away when you do this calculation. And in that case, the region of convergence expands out to the next pole, for example. All right, that will become more clear as we work out examples. Now, for the derivative property, region of convergence, there's no change in general, unless a pole gets canceled. This might cancel a pole at 0, and that would expand the region of convergence larger. This integral property does change the region of convergence. The new region of convergence is the intersection of the old one and the set of s's where the real part is positive. Okay, so the new region of convergence can only have s's with real parts being greater than 0. So you get that intersection. For the time shift properties, you get no change to the region of convergence. Okay, so let's look at an example of a z-transform here. Let's take this signal. It's a very simple signal, 2 delta functions. So it's plotted here, and it's a finite duration signal, right? It's 0 everything above 2 in time and everything below -1. So it's a finite duration signal. It should have a very simple region of convergence. To calculate the z-transform, we can plug it right into this sum, and we can use the sifting property. So the sifting property says, let's first consider this first delta function, because linearity says we can do this at 2 separate sums. So this delta n times z to the -n, if we do that sum, we just plug in 0 for n here. We get z to the 0 is 1. So that becomes 1. For the second term, let's take the -2 out. Then we take a delta of n minus 1 times z to the -n, and we sum that. The sifting property says we should plug in 1 for n. So z to the -1. So what we get here is a z to the -1. This actually will become, very quickly, this becomes very intuitive. If you have a finite duration discrete time signal, you just take each term separately, each delta function, and it becomes a single term by linearity. And it's very easy to see that the delta function just becomes a z to a power, and that power is exactly the delay of the delta function. Okay, so this became z to the 0. This became z to the -1. All right, it's that simple to do the z-transform of a finite duration signal. That's extremely easy. Now, is this rational? Well, it is, and if you have trouble seeing that this is rational as written, you can write it this way. And now we see that, because maybe you were not happy about seeing negative exponents, fine. Then now every z has a positive integer exponent here, and this is certainly rational. In fact, it has 1 0 and 1 pole. The 0 is at z equals 2, and the pole is at z equals 0. So this plot of the z domain, this is a pole 0 plot for that signal. It has a 0 at 2 and a pole at 0. And this tells you the entire z-transform up to a scaling constant. Okay, remember, the only thing this doesn't say about the rational function is the scaling constant. In this case, the scaling constant is in fact 1. Okay, but so essentially, aside from the scaling constant, this thing identifies your signal. Of course, you would also need to know the region of convergence, but for this particular pole 0 plot, there's only one region of convergence. It's the whole space, except for z equals 0. Okay, so let's talk about those regions of convergence. We know that for rational z-transforms, the poles are the boundaries of the region of convergence. But here, remember, regions of convergence are rings. So in this example, it's a little hard to see when it's already drawn out. But this example, I have the black is the unit circle. And I have 3 poles in red here and 2 zeros. So I draw out for those poles and zeros which regions of convergence could exist. there are three different signals because there are three different regions of convergence. Let's draw them out. You have a region of convergence inside the innermost poles. Okay, that's this light blue. You have one between the poles. That's this purple. And you have one outside of this pole here. So I chose these poles to be exactly at the same radius. All right, that's why we don't have anything between them. Okay, so there are three different regions of convergence. That means there are three different signals that could all have this same this same pole zero plot of the Z transform. Now let's see what we know about each of these. For the blue one, this is a left-sided signal and it's not stable. The reason we know that is left-sided because it's inside. It has no inner boundary. Okay, so that means it's left-sided. And it's not stable because the unit circle, this black, is not in the region of convergence. Okay, then we have, so a left-sided not stable system, you think of something that goes to the left and is growing. As it goes to the left, it keeps growing. Now this purple one, this has boundaries outward and inward. So this is a two-sided signal. It's neither left-sided, neither right-sided, mathematically speaking. So it's two-sided, but it's actually stable because the unit circle is in the region of convergence. So think of this as something sort of like sync. It's two-sided. It goes on in both directions, but it doesn't grow. It shrinks. In fact, we know for this signal it's actually going to shrink much faster than sync does. It's going to exponentially decay in both directions. And we know that because this region of convergence is not just the unit circle. It's outside the unit circle. That means you could even multiply it by, for example, a growing exponential function, and it would still converge up to a certain exponent. Okay, then the green is a right-sided signal because it has no outward boundary. It's not stable because the unit circle is not in it. And we'll talk about causality in a second. But out of all of the signals that have the same pole zero plot, only one of them could be stable, right? Because only one can contain a unit circle. Now let's talk about causality. We talked about, we know that by definition, a causal signal is, a causal system which has a causal impulse response, right? So let's just talk about that as a causal signal, implies right-sided. Causal implies right-sided, okay? That's just by definition. Now, we know that what I didn't really emphasize in the Laplace transform was that right-sided, if it's a rational Laplace transform, then right-sided will also correspond to causal. So they'll be equivalent for rational Laplace transforms, okay? Let's look at the Z transform here, and let's assume we have a rational Z transform. So this property only holds for rational Z transforms. Then we have that right-sided does imply causal if and only if the number of zeros is less than the number of poles. So that's interesting because that's something we don't have in the Laplace transform. We actually have to go count poles and zeros. And I don't mean poles and zeros that are in the region of convergence. Here it has nothing to do with the region of convergence. Just look at all the poles and zeros. And in this case, we have 3 poles and 2 zeros. So this condition is in fact true, which means that the right-sided signal here, the green one, is not only right-sided, it's actually causal. Okay? If we had more zeros than poles, then even though the green one is right-sided, it would not be causal. Okay? And I wanted to kind of justify why that happened, so this last little comments here are just kind of to give you maybe some intuition for why this condition has to hold in the Z transform. All right, first of all, here's an example. Here's a signal that's very simple, that's non-causal but right-sided. Okay, so it's so here it is plotted in time. It's right-sided because it's off to the left. There is a point where it stops. Right after -2, after n equals -2 to the left, it's all 0. So that makes it right-sided. But it's not causal because the impulse response of a causal system has to be 0 for all negative values of n. And this n equals -1, it's non-zero. Okay, so when we take the Z transform, we get that the Z transform is just Z. And Z has exactly 1, 0, and 0 poles. So that corresponds to our theorem up here, that the number of zeros here is greater than the number of poles, and it's and in this case it's right-sided but non-causal. Okay, now here's, hopefully this will be meaningful to some people, further justification for why this holds. If we assume xn is non-causal, then we know that the z transform, which is expressed this way, there will be some terms where non-causal means that there are some negative values of n for which this is non-zero. So in other words, there exists some positive k for which x of negative k is non-zero. And that's going to correspond, in this sum, that's going to be a term, a non-zero term here, times a z to a positive number, a positive k, plus all the other terms in this sum, right? But what you'll notice is when you put all this together and you put it into a single fraction to make a rational function of a polynomial over a polynomial, the order of the numerator is going to be greater than the order of the denominator because there is this z to a positive number here. So that means the number of zeros will be greater than the number of poles. All right, that was just, again, to just sort of justify this relationship here. Remember that if it's the Laplace transform, not the z transform, then you don't have to worry about the number of poles and zeros. If it's a rational Laplace transform, then right-sided and causal will be equivalent.